Alright, let's proceed. So last time we were able to talk about electric power. One of our concerns with regards to electric power is an efficient way of storing energy. Even up to now, there is no perfect, no single ideal that has been turned into reality on how we store our energy. But one of the reliable components or devices to which we store our energy or electric power is batteries. So batteries, they have been around for a while now and there is still continued research about them. But one important property we have to consider is its internal resistance. Okay. Now batteries, we have observed that they have a certain voltage being declared. And that is actually what we refer to as the electromotive force or EMF. This EMF or electromotive force is said to be the maximum voltage that this battery have. So for example, if you say you have 1.5 volts battery, then this battery will not exceed this voltage in terms of its ability or capacity to supply. Okay. However, in reality, we do not expect this 1.5 voltage or volts because it is expected to decline over time, so with usage and its internal resistance. So this internal resistance is the reason why if you try to test a battery for its current or voltage, then you do not expect a perfect 1.5, for example. Okay. Now the actual voltage that we measure or that is supplied is what we refer to as the terminal voltage, usually denoted by V from A to B. Now this is the difference between EMF minus a current that can be drawn from this battery times the internal resistance. So it is expected that terminal voltage is less than the EMF of the battery. So for example, if we have a 65 ohm resistor connected to the terminals of a battery with EMF 12 volts and the internal resistance is zero point 0.5 ohms, what is the current in the circuit, the terminal voltage of the battery, and the power dissipated in the resistor R, and of course in the battery's internal resistance. So what we'll do here, let's try to visualize our circuit. So we have a 65 ohm circuit, resistor, connected across a 12 volts battery. But this battery has an internal resistance. And we're going to consider that as another. So represent it as another resistor. So this will be small m, R. This is 0.5 ohms. And this is big R, 65 ohms. Where the EMF of this battery is 12 volts. We need to know the current and the terminal voltage. But we know EMF, internal resistance, and big R, the value of this resistor across. Okay. Now what we can do here is to try to relate. So we have two unknowns. So we try to relate this equation, and of course, we can use Ohm's law, where the voltage across a resistor is the product of the current flowing through it and its resistance. So we can use this to find terminal voltage because we can get the current that can pass through the resistor. Because remember that we remember that our series connection, or rather, these are just put together by series, so no other components in between. So we know that we can use this law. Okay. We can assume that the current flowing through is more or less the same for now. Okay. So let's try to plug in. So what we'll do here is we're going to substitute this term here. Okay, V here is terminal voltage. So rather, the voltage is same for now. Okay, now we'll do IR equals E minus I times small r. So transposing, this becomes I big R plus small r. And then we can get current, where current is equal to 12 volts over 65 plus 0.5 ohms. And if you try to notice, it's as if we've been treating the internal resistance as another resistor. And if we're going to calculate, so 12 over 65.5, we'll get 0. So this is 0.183 amperes. Now that we have the current in the circuit, we can get now the terminal voltage. So terminal voltage is 12 minus 0.183 times internal resistance. And this is equal to so we have here 11.91 volts, which is more or less close to our electromotive force because we have a small internal resistance. Now we recall from our previous discussion that power is just the product of current and voltage. So we can now find power dissipated in the resistor big R and power dissipated in the battery's internal resistance. So P sub R, so big R. Now we know that we have the current, which is 0.183 times a big resistance. So that is 65 ohms. Rather, the voltage, we don't know the voltage yet, not the resistance, sorry. So we have to express this first in terms of resistance, where V is just the ratio between, or rather the product of current and resistance. So we have I squared R. So this will be 0.183 amperes squared times 65 ohms. This will be equal to this should be equal to 2.18 watts. And we see that with this big value of resistance, so we have quite a magnitude of power. Let's compare with the battery with smaller resistance. Okay, so we simply multiply the current and the internal resistance 0.5, and we should get 0.017 watts. And we see that the greater resistance you have, the more power required to dissipate or to be dissipated. Okay. Now let's talk about resistors in series and parallel. So recalling, so earlier we have had already some overview about circuits and components. Okay, particularly how we arrange capacitors, how we arrange resistors. Now we can have combinations of series and parallel circuits, and we have to take note that it's Ohm's law that still governs this combination of series and parallel circuits, we still use Ohm's law. Okay. So for series, purely series, we know that voltage, the total voltage in a circuit, is the sum of the voltage across each resistor. Okay. Okay, so sum of the voltage of the resistors. Okay. Meanwhile, the current, okay, for series, the current is just equal to each component. So all currents passing through the component is equal. Meanwhile, for the total resistance in a series circuit, this is the sum of the resistances. Alright? For parallel circuits, so the total voltage is equal all throughout. Okay. It's uniformly distributed. And then for the current, it is the summation of all the currents in passing through the different components in a circuit. Lastly, for resistance, in parallel circuits, this is the reciprocal of the sum of the reciprocal of the resistance values. So say for example, you have two resistors. So the in parallel, the total resistance is said to be, so the sum of the reciprocal for each value. Okay. So the reciprocal of the sum of the reciprocal. Okay. Because if you were to think about it, it is originally like expressed in this manner. And so on and so forth. So that's why we have to raise this summation to -1. So for example, we have this circuit. How much current is drawn from the battery and how much current passes through each resistor? What we can do here first is to try to assess. So it's easier if we simplify first the combination. And we can do that by finding equivalent resistance, particularly for these two resistances here. So let's try to name this. Consider this R1, R2, and consider this R3. First thing we have to do is to find this equivalent resistance. So let's name this R equivalent to 1, 2. Since these two are in parallel, so we can say, okay, that equivalent resistance is 1 over 500 ohms plus 1 over 700 ohms to the -1. And this will be equal to, so always remember to raise it to -1. So we have here is approximately, if not equal to, 292 ohms. So this is now 292 ohms. Next thing to do would be, we have to find again the equivalent. In other words, total. Because we need to know the total current drawn from the battery. So RT, so let's just consider the modified circuit. RT is sum of R3 and R equivalent 1, 2. So this will be equal to 692 ohms. And from this, we can now find the current. Simply divide the current by the total resistance. Total resistance of 692 ohms. So, current is equal to 0.017 0.34 amperes. Okay, this is the current drawn from the battery of 12 volts. Next would be how much current will pass through each resistor. So one thing we can do here is so let's just stick with the modified circuit first. So current passing through resistor 3. So since this is in series, so the modified circuit is in series, this is said to be equal to the total current drawn from the battery, and this is also equal to the current that will pass through the equivalent resistance 1, 2. Okay, so in other words, I3 is just equal to 0.01734 amperes. Now, to get the specific current, so I1 and I2, now we have to consider now the parallel, so the original circuit. We go back to the original circuit. Okay, but what we can do here is that since we know the equivalent resistance in terms of series, so we have to make sure that the sum of I1 and I2 is equal to this current. What we can do here is let's try first to determine the voltage drop from terminal A to B. And then that will be the voltage that will enter, so this node here, towards the parallel resistors. So we know that voltage across 1 is equal to, so 0.01734 times 400 ohms. And then we'll be able to determine voltage drop that will enter V2. So V2 is equal to 12 minus V1. Okay. Now, V1, voltage, rather V3, this is V3. Voltage across resistor 3. So let's try to compute. This is 6.94 volts. Now, we will know now the voltage that will pass through equivalent resistor 1, 2. That is 12 minus 6.94. 5.06 volts. Now we know that this is 5.06 volts. So it will pass through. We can use this to get I1 and I2. So I1 is equal to 5.06 over 500 ohms. I2, 5.06 over 700 ohms. So we have here this 0.01012 amperes. And the other one is, we have 0.00723 amperes. And if we try to add these two, so that will be approximately, if not equal to, so this is approximately 0.01734. Okay, so this is now our final answer.